Calculus students, this video is going to cover absolute convergence and the ratio and root tests. So first let's discuss absolute convergence. The definition is as follows. We say that the sum of an converges absolutely if the sum of the absolute value of an converges. So basically, when you take the absolute value of all of the terms and you sum them up, if that infinite series converges, then we say the original series converges absolutely. Definition number 2, conditional convergence. We say that a series, sum of an, converges conditionally if it converges, but not absolutely. So a series converges conditionally if it just converges as is, but not when you take the absolute value of the terms and sum them all up. Okay, so we're going to determine whether the following series in example 1 is absolutely convergent, conditionally convergent, or divergent. You always want to test first for absolute convergence. We'll get into why in just a minute, but that's how I'm going to begin this problem. So I'm going to test for absolute convergence. So in that case, I'm going to consider the sum, n equals 1 to infinity, of the absolute value of an. And this would give me the sum, n equals 1 to infinity. Now, if I take the absolute value of these terms here, then the alternating portion, negative 1 to the n, will go away, right? It'll all become positive. So I'm just going to be left with 1 over n. Well, I don't even need to apply a test. I already know what's going on here. This is the harmonic series. What do we know about the harmonic series? This one is divergent. So what does that tell me about my original series? It is not absolutely convergent. The sum of the absolute value of the terms does not converge, so our original series is not absolutely convergent. However, does it converge conditionally? That's what I'm going to check now. So I'm going to test for conditional convergence. So when you're testing for conditional convergence, you just test whether the original series, sum of an, converges as is, the way it was originally written. So we have the sum, n equals 1 to infinity, negative 1 to the n, times 1 over n. Now, what test do I need to apply here? Well, this is an alternating series, so I'm going to apply the alternating series test. So using the AST, first thing I want to show is that the terms are decreasing. Can I show b sub n plus 1 is less than or equal to b sub n? Well, b sub n plus 1, remember b sub n is just 1 over n. That would be 1 over n plus 1, and clearly that's less than 1 over n since the denominator is larger, which is b sub n. So first condition is satisfied. Second condition, can I show that the limit as n approaches infinity of b sub n is 0? Well, let's see here. We have the limit as n approaches infinity of 1 over n, and clearly that's going to go to 0. Denominator gets arbitrarily large. So both conditions are satisfied for the AST, which means that the series converges. Therefore, I can say that my original series, the sum n equals 1 to infinity of negative 1 to the n times 1 over n, converges conditionally. Right? Since it did not converge absolutely, but it did pass when I test for conditional convergence, when I tested convergence of the original series, then I say it converges conditionally. All right. Now, the next theorem is going to explain why you always should test for absolute convergence first. And it states the following. If the sum of an converges absolutely, then that means it converges. So basically, absolute convergence is the strongest type of convergence there is. If you take the absolute value of the terms, meaning none of them are negative, and you sum them up and the series converges, then for sure, without taking the absolute value, if some of the terms are negative and you add them up, that series will converge. If anything, it's going to help it shrink faster. So that's why you always want to test for absolute convergence first, because if you have absolute convergence, then you're done. You don't have to test for conditional convergence. So notice here, absolute convergence, just in summary, means that the sum of the absolute value of an converges, and therefore your original series, the sum of an, converges as well. Conditional convergence happens when the sum of the absolute value of an diverges, but the original converges, all right? And then you can still have divergence. If the absolute value of an, that sum diverges, and the original series diverges, then it just diverges and you're done. Okay, so let's look at another example so we can get a feel for how to apply this testing criteria. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. So we have the sum n equals 1 to infinity of negative 1 to the n over n to the fourth. So what do I test for first? Always absolute convergence. So test for absolute convergence. So we have the sum, n equals 1 to infinity, and I'm going to test what the sum of the absolute value of an is going to do. So that's going to be the sum, n equals 1 to infinity. Absolute value of an is just going to be 1 over n to the fourth. Well, what can I say about this sum? Well, this is a p series, right? P series, p is equal to 4, which is greater than 1, which means it converges. Therefore, the sum, n equals 1 to infinity, of negative 1 to the n times 1 over n to the fourth converges absolutely. All right, and then I'm done. So you don't want to waste your time testing for conditional convergence doing AST, it passes, because then you're still going to have to test for absolute convergence afterwards. So go for absolute convergence first, because if it passes, then basically you've completed the problem. Okay? Let's look at another example now and see what other sort of situations can arise. So example 3, determine whether the series is absolutely convergent, conditionally convergent, or divergent. Okay? So to start off, I'm going to test for absolute convergence first. So I'm going to test for the convergence of the sum n equals 1 to infinity of the absolute value of an, which is the sum n equals 1 to infinity. You can just drop that negative 1 to the power part, right? When you take the absolute value of the terms. So this is going to be 2 to the n over n to the fourth. All right, well, this isn't a typical P series or geometric or something else. It's kind of a mix, right? And notice the numerator, 2 to the n, that's growing exponentially. And the denominator is n to the fourth. And we know an exponential function always grows faster than any polynomial. So I have a feeling that the numerator is growing faster than the denominator. And if that's the case, then that means the terms are not even shrinking. And if the terms aren't shrinking, an isn't shrinking, it's not going to 0, then for sure this series won't converge because it'll fail the test for divergence. So let's see if we can apply that test here. The test for divergence, remember, is when we look at what the limit is of an. And in this case, to take this limit, I'm going to want to apply L'Hopital's rule. So first I have to define a function in order to do that. So I'm going to let f of x equal 2 to the x over x to the fourth. So let's consider the limit as x approaches infinity of 2 to the x over x to the fourth. Well, the numerator is approaching infinity, denominator is approaching infinity, so I have an indeterminate form of the type infinity over infinity. So we can apply L'Hopital's rule. I'm going to have the limit as x approaches infinity. Derivative of 2 to the x is going to be 2 to the x times natural log of 2. Derivative of x to the fourth is 4x cubed. I still have indeterminate form of the type infinity over infinity. So let's apply L'Hopital's rule again. So this is going to be the limit, x approaches infinity. Derivative of 2 to the x is 2 to the x times ln of 2, and then I have another ln of 2 over, now derivative of 4x cubed is going to be 12x squared. All right, I still have indeterminate form of the type infinity over infinity, so we'll apply L'Hopital's rule again. I have the limit, x approaches infinity. Derivative of the numerator is going to be 2 to the x times ln of 2 cubed, and then I have 24x in the denominator. And then I need one more iteration of L'Hopital's rule, right? Or maybe you can already see what's happening. So the denominator is going to become a constant. The numerator will always have 2 to the x, and then these ln of 2's will keep accumulating, and I'm left with 24. So the numerator is approaching infinity, denominator is a constant, so this limit is infinity, which is not 0, not even close. So what does this tell me? Well, my series doesn't converge absolutely. All right. Well, that means it does not pass the test for absolute convergence. Shall we test for conditional convergence? Well, when you test for conditional convergence, you apply the AST, right? And from above, we already showed that the limit as n approaches infinity of b sub n, right? Because b sub n is equal to the absolute value of a sub n, this limit is infinity, not 0, which means that already I know this series fails condition 2 for the alternating series test. Well, what do we do when that happens? Typically, we end up having to just apply the test for divergence. And what can I say? Well, in this case, I'm applying the test for divergence to the original series, the original a sub n, not the absolute value of a sub n. This means that the limit as n approaches infinity of a sub n actually does not exist. And as we've discussed before, this is because the even terms approach one limit and the odd terms approach a different limit. Now notice our original a sub n was -1 to the n minus 1 times 2 to the n over n to the fourth. So the even terms are going to have -1 raised to an odd power. So the even terms are going to be the ones that approach negative infinity, and the odd terms are going to be the ones that approach positive infinity. And this means that the limit as n approaches infinity of a sub n does not exist. So I can conclude, therefore, the sum n equals 1 to infinity of -1 to the n minus 1 times 2 to the n over n to the fourth diverges by the test for divergence. Okay. Now, right here is where a bunch of students will ask me, if I notice that, do I have to even go through the beginning part of the test, testing for absolute convergence, to begin with? And the answer is no, you don't need to. So if you look at your series, okay, from the very beginning, let's look at this. And you're asked to test for absolute conditional convergence or find if it's going to diverge. And you already notice, hey, these terms are not shrinking. They're not going to 0. And you just want to go straight to the test for divergence and say the odd terms are going to one place, the even terms are going to another place. Therefore, limit as n approaches infinity of a sub n does not exist. So the series diverges by the test for divergence, you can totally go for it, okay? I just wanted to work through what the process would be like if you didn't happen to notice that at first glance, okay? But if you're very observant, then feel free, because ultimately the crux of the solution comes down to this portion here. And of course, you'd have to justify and show this limit clearly as well. All right? Good. Hopefully, as we work through more examples too, the process will get a little bit more clear. All right, so let's review what we've covered so far. First, if the limit as n approaches infinity of an, if the terms of my series do not approach 0, then automatically we know the series is divergent by the test for divergence. Next, if the terms do approach 0, so if the limit as n approaches infinity of an is 0, we have no information. The series could be convergent or divergent. We still need to apply another test. The best example to keep in mind, to remind you of this fact, is the harmonic series. The terms 1 over n approach 0, but the harmonic series is divergent. All right, and then lastly, for an alternating series, we consider the absolute value of an, which is bn, and if the limit as n approaches infinity of bn is 0, and the terms are decreasing, so b sub n plus 1 is less than or equal to bn, then we have a convergent alternating series. All right, now let's add to our bag of tricks the ratio test. So far we've covered the integral test, we have the alternating series test, and then at the very beginning of our study of series, we consider geometric and telescoping series to determine whether a series converges or diverges. And now we have a new test, the ratio test. So the ratio test states that if we have the sum of n equals 1 to infinity, then if we take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and that limit is less than 1, then that means the sum of an converges absolutely. All right. If you take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and that limit is greater than 1, then the sum of an diverges. And if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to 1, then the ratio test fails. It's inconclusive. So it doesn't mean you're done. It means you need to apply a different test, that the ratio test was not an appropriate choice for the series that you're trying to analyze. Okay, and the statement should make sense, because when you take this ratio, a sub n plus 1 over a sub n, right, that's the ratio of one term over the preceding term. So as long as it's decreasing fast enough, then this ratio will be less than 1, and that means that the series will converge. Okay, make sure when you're applying the test too, you write out the statement and you mention that that's the test you applied. So just watch to how I write out the solutions in the next few examples. Okay, so use the ratio test to determine whether the series is convergent or divergent. So we have the sum n equals 1 to infinity of n squared over 2 to the n. So they're telling us to use the ratio test later on. They're not going to be so nice. So we have the limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n. So this is equal to the limit as n approaches infinity, and I'm going to have the absolute value. A sub n plus 1 is going to be n plus 1 squared over 2 to the n plus 1 over a sub n, which is just n squared over 2 to the n. Okay, now I don't really need these absolute value bars. None of the terms are negative here. So I can just drop them, and I'm going to rewrite this as the limit as n approaches infinity of n plus 1 squared over 2 to the n plus 1 times, now 2 to the n is going to flip up to the numerator here, over n squared. Okay, now I want to simplify this expression before I evaluate the limit. So I have the limit as n approaches infinity. We have here n plus 1 squared. 2 to the n plus 1 I can write as 2 to the n times 2, right, to the first. That would give me 2 to the n plus 1 times 2 to the n over n squared. Now I wanted to break up 2 to the n plus 1 that way so I could cancel out this 2 to the n here. Okay, And then also notice I can take this 2 outside of my limit. It's just a constant. So I can rewrite what I have now as 1/2 times the limit as n approaches infinity. N plus 1 quantity squared, I can expand that into n squared plus 2n plus 1. And then all I'm left with in the denominator is this n squared. Okay. Now let's evaluate this limit. Notice the highest degree in the numerator is 2, highest degree in the denominator is 2. So again, I'm just going to take the ratio of the leading coefficients, and that's going to give me 1. So the limit of this expression as n approaches infinity is 1. And so I'm left with just 1/2 times 1, which is 1/2. Well, since I'm using the ratio test, I always want to compare this number to 1, and 1/2 is less than 1. You have to write this inequality after you take the limit, either less than 1 or greater than 1, to show that you understand what the statement of the ratio test entails. And what does this tell me? Well, it tells me that the sum n equals 1 to infinity of n squared over 2 to the n converges by the ratio test. Okay. And the problem only asked for me to determine whether the series was convergent or divergent. But remember, when applying the ratio test, if the series converges, it also converges absolutely. They didn't ask for that, but that's just our little PS. I really know what's going on, if you feel like writing it. Okay. Do you like the ratio test? It's usually pretty fun. Let's look at another example here. The ratio test again is going to be used to determine whether the series is convergent or divergent. And notice here we have the sum n equals 1 to infinity of n factorial over 100 to the n. Even if they didn't tell us to use the ratio test, most of the time when you see a factorial in the terms, you want to use it. And you'll see why right now. So we have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And here, I'm going to write out the limit as n approaches infinity. Now I don't need the absolute value. None of the terms are negative, right? A sub n plus 1 is going to be n plus 1 factorial divided by 100 to the n plus 1. And then this is all over n factorial over 100 to the n. All right, now let's clean things up a little bit. So I have the limit as n approaches infinity. Now, n plus 1 factorial, I want to break it up and write it as n plus 1 times n factorial over, and then 100 to the n plus 1, I'm going to break it up just like I broke up 2 to the n plus 1 in the last problem. So I have 100 to the n times 100. So this is just the numerator here being rewritten because I'm getting ready to cancel stuff. And then I'm going to multiply that by 100 to the n over n factorial. Okay? So see here, the n factorial cancels out so nicely because we applied the ratio test. So I just have that little n plus 1 surviving in the numerator. And then I can also cancel out 100 to the n. All right. And then similarly to last time, if you want to pull that 100 outside of the limit, you can do so. So this is going to be 1 over 100 times the limit as n approaches infinity. Now what's left over? Just that n plus 1. Well, my goodness, when n approaches infinity, n plus 1 also approaches infinity. And even if I multiply by 1 over 100, it's still going to be infinity. So this limit is infinity. And what can I say about it? Well, that's definitely greater than 1. So the sum, n equals 1 to infinity of n factorial over 100 to the n, diverges by the ratio test. Yes, you have to write that even though they told you to use the ratio test. Just get in the habit to always write that out. What test you used. All right, nice. Ready to add another test to your bag of tricks? So the next test in this section is the root test. So given the sum of an, if the limit as n approaches infinity of the absolute value of an, the nth root, so the root test states the following. Given the sum of an, if the limit as n approaches infinity of the nth root of the absolute value of an is less than 1, then that means the sum of an converges absolutely. If the limit as n approaches infinity of the nth root of the absolute value of an is greater than 1, then the sum of an diverges. And, similar to the ratio test, if the limit as n approaches infinity of the nth root of the absolute value of an equals 1, then the root test fails. So what that means is you need to apply a different test. Okay. Example 1. Use the root test to determine whether the series is convergent or divergent. So I'm going to do as I'm told. Apply the limit as n approaches infinity of the nth root of the absolute value of an. So this is going to be the limit as n approaches infinity. I'm going to have the nth root of, and then now if I take the absolute value of an, I won't have a negative in the numerator anymore. So I'm just going to have 2n over n plus 1 raised to the 5n. And you'll see the root test is a perfect test to apply to this particular series because when I take the nth root of 5n, remember you're just basically dividing the exponent by the index. So I'm going to be left with the limit as n approaches infinity of 2n over n plus 1 raised to the 5th. Okay. Well, now let's see, how can we evaluate this limit? Well, 2 is being raised to the 5th power, so I can pull that outside of my limit. So this is going to be 32 times the limit as n approaches infinity of n to the 5th over n plus 1 to the 5th. Now, how do we take this limit? Notice the denominator is not expanded. N plus 1, that quantity is raised to the 5th, and I'm not about to multiply that out. So what I'm going to do is divide out by the highest power of n in the denominator. So I'm going to multiply here by 1 over n to the 5th, 1 over n to the 5th. All right, so what are we going to be left with? We still have 32 out here, the limit as n approaches infinity. Now in the numerator, I'm just going to have n to the 5th over n to the 5th, so that's 1. And then now when I distribute 1 over n to the 5th to the quantity n plus 1 raised to the 5th, I have to basically take the 5th root when I put it inside the parentheses. So I'm going to have n over n, which is going to be 1 plus 1 over n raised to the 5th. And then now I can take this limit. So as n approaches infinity, 1 over n, that's going to approach 0. So this quantity here is just going to be approaching 1, and I have 32 on the outside. So this limit's going to be 32 times 1, which is 32, and that's definitely greater than 1. So what does that tell me? That tells me that the sum, n equals 2 to infinity, of negative 2n over n plus 1 to the 5n diverges by the root test. All right, looks good. Let's consider another example here. Example 2. Use the root test to determine whether the series is convergent or divergent. So we have the sum n equals 1 to infinity of 1 plus 1 over n all raised to the n squared. So we're going to consider the limit as n approaches infinity of the nth root of the absolute value of an. Well, taking the absolute value is not going to do anything, so I'm just going to write an as it is, 1 plus 1 over n to the n squared. Now I'm going to take the limit as n approaches infinity, and this is going to be 1 plus 1 over n raised to the n squared, and then this is all raised to the 1 over n, right? And then when I take an exponent and I raise it to another power, I end up multiplying them. So n squared times 1 over n is just going to give me n. So now I'm left with the limit as n approaches infinity of 1 plus 1 over n raised to the n. Do you know what this limit is? This one's a famous one. This is e. Oh my goodness. And e is about 2.7, which is bigger than 1. So this means that the sum, n equals 1 to infinity, of 1 plus 1 over n raised to the n squared diverges by the root test. Okay? Good. Now don't have a meltdown if you're saying, I totally forgot that that limit was e, it's been a while, what would I do if I didn't recognize it? Well, I'll show you right now. So recall, there are 7 indeterminate forms. All right. The first 2 of the type 0 over 0 or infinity over infinity, they are already set up for you to apply L'Hopital's rule. If you have the type 0 times infinity or infinity minus infinity, you need to rewrite these somehow so that you can apply L'Hopital's rule, usually. And then the last 3 types are indeterminate powers, 1 to the infinity, 0 to the 0, or infinity to the 0. All of these, you take the natural log of them, and then you can apply L'Hopital's rule. Okay, so I'm going to show you how we could evaluate the limit up above if you didn't recognize that it was e. Okay, so first thing, if I'm going to want to apply L'Hopital's rule, remember I have to redefine a function using x because it needs to be differentiable. So we're going to consider the limit as x approaches infinity of 1 plus 1 over x to the x. And I can see I have an indeterminate form of the type 1 to the infinity. So what I'm going to do is let y equal 1 plus 1 over x raised to the x. And then now I'm going to take the natural log of y, which would also equal the natural log of 1 plus 1 over x to the x, which I can rewrite as x times the natural log of 1 plus 1 over x. And so instead of taking the original limit, I want to actually consider the limit as x approaches infinity of the natural log of y, which is the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. And now I have an indeterminate form of the type infinity times ln of 1 is 0. But this I can easily rewrite, so I can apply L'Hopital's rule. I'm going to just simply put the x in the denominator as 1 over x. So I'm going to rewrite this now as the limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over x. Now, do I have one of the indeterminate forms of the type where I can apply L'Hopital's rule? Let's see. So x goes to infinity. I have ln of 1 in the numerator, so that's going to 0. X goes to infinity, denominator is going to 0. So yes, I'm allowed to apply L'Hopital's rule. So now this is going to be the limit as x approaches infinity. Derivative of the numerator, derivative of ln of 1 plus 1 over x is going to be 1 over 1 plus 1 over x. And then by the chain rule, I need to multiply by the derivative of the argument, 1 plus 1 over x. Derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. And then in the denominator, I need to take the derivative of 1 over x, which is just negative 1 over x squared. All right, this is looking nice because negative 1 over x squared is just going to cancel out. Great. So then now I'm left with the limit as x approaches infinity of 1 over 1 plus 1 over x. And then I can just take this limit directly. 1 in the numerator is a constant. In the denominator, 1 is a constant. 1 over x, as x approaches infinity, this is going to go to 0. So my limit's just going to be 1 over 1, which is 1. This tells me that the limit as x approaches infinity of the natural log of y was 1. So my original limit as x approaches infinity of 1 plus 1 over x to the x is going to be e raised to the limit as x approaches infinity of the natural log of y, which is going to be e to the first, since that limit was 1, which is e. Okay? So basically, at the end of this whole process, when you take the natural log, in order to evaluate the limit, whatever result you get, you just have to take e and raise it to that power to get back the limit for the original expression, okay? So there you go. You may need to apply that for some of your other applications involving the root test. Last example, test the convergence of the following series. We have the sum n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the n. So I have the limit as n approaches infinity of the nth root of the absolute value of an. Well, an doesn't have any negative terms, so I'm not going to write the absolute value. So we just have 2n plus 3 over 3n plus 2 raised to the n. Well, this is looking good already. The nth root and the nth exponent here are going to cancel out. So I just have the limit as n approaches infinity of 2n plus 3 over 3n plus 2. And compared to that last problem, this limit's a breeze. Highest degree in the numerator is 1, highest degree in the denominator is 1. So I'm just going to take the ratio of the leading coefficients. So that's 2/3. And yay, 2/3 is less than 1. We finally got one that's going to converge. So this tells me that always rewrite your original series, sum of n equals 1 to infinity of 2n plus 3 over 3n plus 2 raised to the n converges by the root test. And in fact, we know that it converges absolutely if you were asked for such information. So that concludes the video. Stay tuned as we look at more tests and more interesting things about series to come.